Good evening. Settle yourself into a comfortable position and let your breathing find an easy pace. Tonight, we are going to spend some time with the moon, not as a distant ornament in the sky, but as a steady system of motion, gravity, and quiet change. It has been turning above human lives for longer than any calendar, and it will continue without effort long after any one night has passed. If you enjoy this kind of calm science, you can quietly support the channel by subscribing. But there is nothing you need to do right now except rest. And as you listen, you can let the details arrive, and then drift away again, like light moving across a familiar surface. The moon is slowly moving away from Earth, and that gentle recession is lengthening our days. This is not a dramatic motion, but a steady exchange of energy between spin and orbit. Earth rotates, and its oceans respond to the moon's gravity with tides that are slightly misaligned because Earth turns beneath them. That misalignment creates friction, and friction turns a little of Earth's rotational energy into heat. The moon, in turn, gains orbital energy, and so it drifts outward, millimeter by millimeter, year after year. The consequence is quiet but profound. Long ago, days were shorter, and the moon was closer, and the rhythm of the Earth-Moon system ticked at a different pace. In the far future, if the system is left undisturbed, Earth will spin more slowly, the moon will orbit farther out, and the two bodies will settle into a calmer arrangement. It is a reminder that even a familiar night sky is part of an ongoing trade, with time itself being gently reshaped. The moon keeps one face turned toward Earth because tidal forces have slowly synchronized its spin with its orbit. This is often described as the moon always shows the same side, but the deeper story is about how gravity can act like a brake. Early on, the moon would have rotated at its own rate, faster or slower than its monthly circuit. But Earth's gravity raised tidal bulges in the moon's solid body, not in water, but in rock. Those bulges were not perfectly aligned because rock takes time to flex and settle, and that delay creates a torque. Over immense time, that torque drained rotational energy, nudging the moon into a state where one lunar day equals one lunar month. It is not a coincidence and not a choice, but a stable endpoint of a process, and the stability matters. The same lunar hemisphere has been the face of our nights for all of human history, so our myths, calendars, and navigation grew around a companion that never turns away. Even though the moon is locked, we still see a little more than half of it over time, because its motion wobbles in a slow, predictable way. The moon's orbit is not a perfect circle, and it does not move at a perfectly constant speed. When it is closer to Earth, it moves a little faster along its orbit, and when it is farther, it moves a little slower. But its rotation remains almost steady, like a metronome that does not quite match the changing pace of the dance. The result is a gentle rocking called libration. It allows us, from Earth, to peek around the edges, first a little to one side, then a little to the other. There is a quiet comfort in that. The moon is not a flat disk pasted onto the sky. It is a world moving in 3 dimensions, revealing itself in small, regular shifts, like a familiar face turning slightly as it passes through lamplight. The moon's phases are a geometry lesson written in light, and they let you sense the shape of the Earth-Moon-Sun system without doing any sums. The phases are not caused by Earth's shadow, except during an eclipse. Most nights, the moon is lit by the sun, and you are seeing a changing angle between the sunlight and your line of sight. The boundary between day and night on the moon, the terminator, is where the most subtle information hides. Along that line, shadows stretch sideways, and tiny changes in height become visible as long dark threads. A crater rim becomes legible. A ridge becomes a slow curve of shade. When the moon is full, the light falls straight on, and the surface looks flatter, quieter, less textured. So the sky is not only showing you a phase, it is showing you how light behaves across a rough world, and how perspective changes what you can know. The same object can feel sharp and detailed, or soft and smooth, depending only on the angle of illumination. A lunar eclipse can only happen when the moon is near a specific part of its orbit, because its path is tilted relative to Earth's path around the Sun. If the moon orbited exactly in the same plane as Earth's orbit, eclipses would be routine, almost monthly. Instead, the moon's orbit is tipped, so most full moons pass above or below Earth's shadow, and most new moons pass above or below the Sun in the sky. Eclipses become occasional and therefore meaningful. When the alignment is close, Earth's shadow falls across the moon, and something subtle happens to the light. The moon does not vanish into perfect darkness. It often glows a dim red because Earth's atmosphere bends and filters sunlight into the shadow. In that moment, the moon is lit by every sunrise and sunset around the edge of our planet, gathered into a faint coppery wash. The eclipse becomes not a spectacle, but a quiet demonstration that air is not nothing. It is an optical instrument around Earth, shaping light at the scale of worlds. The moon's interior remembers its early heat, and the way it cooled helps explain why its surface is so ancient and so well preserved. On Earth, wind, rain, and plate tectonics continually rework the surface, erasing old scars. On the moon, those processes are mostly absent. There is no global ocean to smooth the land, and no active system of plates to recycle crust into the interior. Instead, the moon cooled, thickened, and became largely rigid. Its volcanic activity surged early, then waned, leaving behind broad plains of dark basalt. Its geological voice grew quieter with time. That quietness is why the surface is such a reliable archive. The moon keeps a long record of impacts and ancient volcanism that Earth has mostly lost. When you look at the lunar face, you are not just seeing landscape. You are seeing an old page that has not been turned, where the ink is still legible. The dark lunar seas, the Maria, are not water, but ancient lava plains that filled low basins after huge impacts reshaped the crust. Those broad, darker patches formed when large impacts punched deep basins into the moon. Later, when the interior still had enough heat, molten rock rose through fractures and flooded those basins, cooling into basalt. The basalt is darker than the highlands and smoother at large scale, so it reads as a different texture from Earth. Yet, it is not softness. It is rock, set hard in place, its surface slowly gardened by micrometeoroids for billions of years. The Maria tell a story about timing. Big impacts arrived, leaving wounds. Then, the moon's interior, still warm enough to respond, poured out lava and sealed the scars into dark plains. It is a kind of geological aftercare, and it hints at a moon that was once more active, more responsive, before it settled into the long stillness we recognize now. The moon's soil, called regolith, is not like Earth's soil, because it is made without water, without biology, and with constant tiny impacts that fracture rock into sharp grains. On Earth, grains are tumbled by rivers, softened by chemistry, rounded by time in water. On the moon, the main sculptor is impact. Dust-sized particles arrive at enormous speeds, striking and splintering the surface. Larger impacts churn deeper layers, mixing old and new material. Over time, the regolith becomes a blanket of crushed rock and glassy fragments. The grains can be jagged because there is little to round them off, and the surface becomes electrically active in sunlight because ultraviolet light and the solar wind can charge fine particles. So, the lunar ground is not passive. It is a chemically and electrically unusual environment, shaped by vacuum, radiation, and mechanical violence so small it can be almost invisible. That is why dust became a practical problem for explorers, not because it was abundant, but because it behaved differently than ordinary dirt. Some regions near the lunar poles may hold ice that can persist for extremely long periods, because there are places where sunlight almost never reaches. The moon's axis is only slightly tilted, so near the poles, the sun skims low around the horizon. In certain craters, the walls cast permanent shadow, and temperatures can remain low enough for water molecules to stay trapped as ice, rather than sublimating away into space. This does not make the moon wet. It makes it selective. A molecule of water delivered by a comet or created by interactions between solar wind and minerals can migrate across the surface in a slow, hopping journey and eventually become cold-trapped in darkness. In a vacuum, with no weather to stir it, that ice can remain for ages, a quiet reserve in a place that feels almost untouched by time. And it changes how we think about the moon as a system, not just a dead rock, but a world that can still sort and store materials according to light and shadow. The footprints left on the moon can last far longer than footprints on Earth, because there is almost no air to erase them, yet the surface is not truly still. A boot print on Earth is a temporary arrangement of grains. Wind, water, and life reorganize it quickly. On the moon, there is no rain to soften edges, and no wind to sweep dust smooth. In that sense, a print can remain crisp for a very long time. But the moon is not perfectly preserved. Micrometeoroids keep arriving, and over long spans, they churn the top layer, slowly blurring sharp details. Radiation darkens and changes exposed surfaces. The lunar environment is quiet, but it is busy in miniature, always tapping, always grinding, always rearranging grains, one impact at a time. So those old tracks are not frozen forever. They are simply being erased by a gentler clock, a slow, patient sandpapering of time. From Earth, the moon appears almost exactly the same size as the sun in the sky because of a particular coincidence of distance and scale. And that coincidence teaches you something about angles. The moon is far smaller than the sun, but it is also far closer, and the two apparent sizes happen to match closely enough that the moon can cover the sun during a total solar eclipse. What matters here is not the objects themselves, but the geometry of vision. Your eyes and brain experience the sky as a dome, and objects as patches on that dome. Apparent size is about angle, not about true size. And the eclipse makes that lesson tangible. A world the size of a small planet can precisely blot out a star, not through power, but through position. It is a quiet reminder that perception is made from relationships, and that in astronomy, distance can be as important as mass. And when you consider that geometry, it becomes easier to feel the moon's orbit not as a circle around us, but as part of a larger motion, because Earth and moon move together around the sun, like two dancers bound by gravity, their shared center of mass drifting smoothly forward. while the moon traces a looping path that is always, in a deeper sense, falling onward. The Earth and Moon do not orbit with Earth as a fixed centre, because both bodies circle a shared point of balance that can sit above Earth's surface. That shared point is called the barycenter, and it is the place where the system's mass effectively balances. Because Earth is much heavier, the barycenter lies within Earth most of the time, but not necessarily at the middle. It can be displaced, so that Earth itself makes a small monthly motion, a subtle wobble, as the moon goes around. In a sense, Earth is always being gently pulled into a companion orbit. This matters because it is the simplest way to understand many moon effects without mysticism. The moon is not tugging at a stationary planet. It is part of a two-body system where both partners move, both respond, and both carry momentum forward through space. And once you feel that, the whole arrangement becomes calmer, more mechanical, more like a clockwork that never needed an audience. The moon's orbit is not steady in a perfectly smooth way, because the sun constantly perturbs it, making the moon's path a three-body compromise. It is tempting to imagine the moon circling Earth in isolation, but the sun's gravity is always present, strong and persistent. The moon is close to Earth, yet it is also moving through the sun's gravitational field, and those influences combine. The result is an orbit that precesses, that slowly rotates its orientation in space. It is a controlled drift rather than a clean circle. This is part of why eclipse seasons come and go, and why the timing of alignments follows longer patterns. The moon, in other words, is not only an Earth satellite, it is also a solar system object whose motion is continually negotiated. And that negotiation is quiet. It does not break the orbit. It simply adds a slow complexity, like a gentle current beneath a steady boat. We can measure the moon's distance with extraordinary precision because astronauts left mirrors on its surface, turning moonlight into a scientific instrument. These mirrors are not shining lamps. They are passive reflectors, designed to send incoming laser light back toward its source. From Earth, scientists fire brief laser pulses and measure the time it takes for the light to return. Over decades, those measurements have traced the moon's gradual recession and the subtle flexing of Earth's rotation, and even small wobbles in the moon's orientation. What is soothing here is the scale of the method. A beam of light, smaller than a fingertip at the source, becomes a thread stretched across space. It touches the moon, returns, and carries a message about distance and time. It turns the Earth-Moon system into something you can listen to with instruments, as if gravity itself were leaving a steady rhythm to be read. The moon's far side is not simply the other half, because its crust and geology are noticeably different, and the reasons likely reach back into the system's early heat. The side we see from Earth has broad dark maria, while the far side has far fewer and more rugged highlands. That difference is not because impacts avoided one hemisphere. It reflects how the moon cooled and how its crust formed. One leading idea is that the far side developed a thicker crust, making it harder for lava to reach the surface later on. Another influence may have been Earth itself, radiating heat toward the near side when both bodies were much hotter and much closer. A warm near side could have stayed molten a little longer, changing how materials separated and solidified. So the moon's two faces are like two chapters of the same early story, written under slightly different conditions. And the fact that we live facing one chapter is not destiny. It is simply how the system settled. Some of the Moon's most influential features are invisible from Earth because they are buried under lava plains, creating gravitational lumps that subtly tug passing spacecraft. These mass concentrations, often called mascons, are regions where dense material lies beneath the surface, commonly associated with large impact basins later filled with basalt. To a spacecraft in low orbit, a mascon is like an unmarked hill in the gravitational landscape. It pulls a little harder than surrounding terrain, changing the orbit over time. Early lunar missions had to learn this the careful way, as orbits drifted and became unstable without obvious cause. The Moon looks serene through a telescope, but to something flying close, it is uneven, textured, and full of hidden weight. And that hidden weight is another kind of memory, preserved inside the body of the Moon, where the past still influences motion in the present. The Moon has moonquakes, and their character is different from earthquakes because the Moon is drier, stiffer, and rings like a struck bell. On Earth, quakes travel through a world filled with water and fractured rock, and energy can be scattered and damped in complex ways. The Moon is different, with no widespread liquid water and a very cold, rigid outer layer. Seismic waves can reverberate longer. Some moonquakes are linked to tidal stresses as the Moon's orbit slightly changes shape, gently flexing the body. Others may come from thermal stresses as surface layers expand and contract. There are also impacts, small and large, that send shocks through the crust. The overall impression is not of a lively, shifting planet, but of a quiet world that still responds, that still creaks and settles, and that carries vibrations through a body that has been cooling for billions of years. Day and night on the Moon are not gentle transitions, because without an atmosphere, the surface swings between intense heating and extreme cold. Air does more than let you breathe. It spreads heat, softens temperature differences, and slows the pace of change. On the Moon, sunlight falls directly onto rock and dust, and when the sun sets, there is little to hold the warmth near the surface. Over the course of a lunar day, the same ground can bake, then freeze, while only a short distance down the soil stays steadier, insulated by its own low conductivity. This creates a world of sharp boundaries. Sunlit ridges can be bright and harsh. Nearby shadows can be bitterly cold. It is an environment designed by vacuum, where the simple presence or absence of light becomes the main climate system. And in that simplicity, there is also clarity, as if nature has removed the softening layers and left the raw physics exposed. In the Moon's airless environment, weathering still happens, but it is driven by radiation and impacts, not by wind or water, changing the colour and reflectivity of the surface over time. The lunar surface is constantly bombarded by tiny particles from space and by the solar wind, a stream of charged particles flowing outward from the sun. These processes can darken and redden surface grains, create glassy coatings, and alter the way light reflects. Freshly exposed material, such as the bright rays around a young crater, can look strikingly different from older ground, not because it is a different rock, but because it has not yet been aged by space. This is called space weathering, and it means the Moon's appearance is a slow record of exposure. Even without air, even without water, time still leaves a patina. It just uses different tools. And because exposure matters so much, the shadows near the poles become more than simple darkness. Because a place that rarely sees sunlight can preserve not only ice, but also a kind of thermal stillness, a quiet stability that is rare on the moon, and in that rare stillness, material can linger, settle, and wait, while above it, the long orbit continues to carry the moon through light. The moon's rotation makes its sunrise and sunset extraordinarily slow, and that slow light changes how landscapes cast shadows and how surfaces warm. On Earth, sunrise feels like a daily event, quick enough that shadows race across the ground. On the moon, a day lasts about a month, so the sun climbs and descends with unhurried patience. A shadow can creep across a crater floor for hours, then days. Rock faces on a slope can heat gradually, and the regolith beneath can lag behind, warming like a thick blanket. This matters for understanding both science and exploration. If you want to study a place by its shadows, the moon is generous with time. The Terminator moves slowly, revealing relief in long, calm strokes. And if you want to work on the surface, the environment is not simply hot or cold. It is a long, drawn-out journey from one to the other, a deliberate turning of a world beneath a steady lamp. The brightness of a full moon is enhanced by an optical effect that makes the surface reflect more light when the sun is directly behind you. This is not just a poetic glow. It is a physical behavior called the opposition effect. At full moon, the sunlight is coming from almost the same direction as your line of sight, so shadows on the moon's surface are hidden behind rocks and grains. The surface looks brighter because you are not seeing as many tiny shadows. There is also a contribution from the way light scatters within the regolith, among grains and glassy fragments, sending light back toward the source more efficiently at that geometry. The result is that full moon brightness is partly about the moon and partly about your viewing angle. It is a gentle reminder that brightness is not only a property of an object, it is also a property of alignment, a quiet cooperation between surface texture and light. The moon's surface is marked by crater rays that fade with time, so their visibility can act as a soft clock for recent geological history. When a meteorite strikes, it excavates material and throws it outward in an expanding pattern. Freshly exposed rock can be brighter than surrounding terrain because it has not yet been darkened by space weathering. Over time, those rays soften and blend. They do not disappear because of erosion by wind or rain. They disappear because radiation and micrometeoroid impacts slowly alter the grains, dulling contrast. So, when you see bold rays around a crater, you are seeing youth in lunar terms, not youth in years like a human lifespan, but youth in a landscape measured against billions of years. The moon offers timekeepers like this, quiet and visual, where recent can mean a span longer than the whole of human civilization. Many lunar craters are not simple bowls, because large impacts make central peaks and terraced walls shaped by the physics of collapse. When an impact is large enough, it does more than dig. It briefly creates a cavity that is too deep and too steep to hold its shape. The floor rebounds upward like a slow-motion splash frozen into rock, and the rim can slump in steps, forming terraces. These structures are a consequence of gravity and strength. They show you that even solid rock can behave like a fluid, given enough energy and a short enough timescale. The moon's craters are therefore not only scars, they are experiments in materials science performed at planetary scale, revealing how the crust deforms under sudden force, and how it settles into a new equilibrium when the violence has passed. The largest impact basins on the moon record a period when the inner solar system was far more crowded with debris, leaving a layered history beneath the surface. Early in the solar system, planets and moons were assembling from a disk of material. That assembly was not neat. It involved collisions, scattered fragments, and bodies that crossed paths again and again. The moon, with its preserved surface, carries evidence of intense bombardment in the form of ancient basins and heavily cratered highlands. Some of the deepest basins were later flooded by lava, but their rings and subtle topography still shape the lunar face. Beneath the surface, these impacts fractured the crust and mixed materials from different depths. So, each basin is not only a hole, it is a rearrangement of the moon's upper layers, a restructuring event that still influences what lies where. The moon is, in this sense, not merely old. It is repeatedly relayered, like a book that has been rebound many times while keeping the same pages. The moon's gravity is strong enough to shape motion and dust, but weak enough that human movement becomes a different kind of balance, revealing how deeply our bodies are tuned to Earth. In reduced gravity, a jump lasts longer. A step carries you farther. The arc of a thrown object is gentler, slower to fall. But the most interesting part is not the spectacle. It is the way the body has to rewrite its instincts. On Earth, your muscles anticipate a certain weight and a certain fall time. On the moon, those expectations are slightly wrong. Movements become buoyant, not because you are floating, but because the same effort produces a different trajectory. This is a quiet lesson in adaptation. It shows how normal is a local condition, how the nervous system is calibrated to one gravitational field. And it also shows that the moon is close enough for us to bring our biology there and notice, directly, the physics that usually stays in the background. The moon's surface is chemically connected to the sun in a subtle way, because the solar wind can implant hydrogen that may help create hydroxyl and water-like signatures in lunar minerals. The solar wind is made of charged particles, including protons that are essentially hydrogen nuclei. When these particles strike the lunar surface, they can embed themselves in the topmost layers of grains. Under the right conditions, that hydrogen can bond with oxygen in minerals, producing hydroxyl groups. From orbit, instruments can detect spectral signatures consistent with this kind of chemistry. It does not mean there are puddles. It means the moon is not chemically isolated. Its surface is in contact with the sun, constantly, as if the star were brushing its face with a thin stream of particles. Over time, this can contribute to a slow cycle, where water-related molecules form, migrate, and in cold traps, collect. The moon becomes not wet, but interactive, participating quietly in solar system chemistry. The moon's lack of a global magnetic field today does not mean it never had one, because ancient lunar rocks suggest a stronger magnetism in the distant past. Magnetism at planetary scale usually implies a dynamo, a churning, conductive interior that sustains a field. The moon is small, and it cooled, and its interior became less active. Yet some lunar samples carry remnant magnetization that hints at a time when the moon had a stronger magnetic environment. The details are still debated, but the possibility is important. It means the moon's interior history may have included a more dynamic phase, perhaps with a partially molten core generating a field for a while, before the engine faded. If so, then the moon's early environment would have been different, with charged particles from space interacting differently with its surface. Again, The theme is quiet change. The moon we see now is not the moon that was. It is the later, cooled, settled version, still holding traces of earlier strength. From Earth, the moon's monthly cycle became a natural clock, but it is an imperfect one, and that imperfection shaped how humans learned to reconcile nature with counting. A lunar month does not fit neatly into a solar year. 12 lunar cycles are a little short of a year, and 13 are too many. So, a purely lunar calendar drifts relative to the seasons unless it is adjusted. Different cultures solve this in different ways, adding intercalary months or combining lunar months with solar observations. The moon, then, is not only a marker of time, it is a teacher of mismatch. It quietly demonstrates that natural cycles do not always align into tidy units, and that any calendar is a negotiation between different rhythms. In that negotiation, you can feel something very human, the desire to make time legible, to turn sky motion into a schedule, and to accept, gently, that the universe does not optimize itself for our convenience. And in the moon's slow cycle, with its slightly imperfect fit to the year, you can sense how measurement itself is a kind of listening, where we choose which rhythm to follow and how to smooth the gaps, while above us the moon keeps moving on its own terms, carrying shadows and light around a world of dust and stone, in a motion that never needs to hurry. The moon helps stabilize Earth's axial tilt, making our planet's long-term climate gentler and more predictable than it might otherwise be. Earth spins with a slight lean, and that lean is not fixed by default. Over long times, gravitational tugs from other bodies can make a planet's axis wander, sometimes dramatically, changing how sunlight is distributed across latitudes and seasons. The moon acts like a steadying weight on a spinning top. Its gravity interacts with Earth's equatorial bulge and alters the way Earth's axis precesses, encouraging a more regular, bounded motion. The result is not perfect stability, but a calmer range of variation. And that calm has consequences. It influences the persistence of seasons, the long-term patterns of ice and warmth, and the slow background in which ecosystems adapt. So, when the moon appears as a quiet disk above you, it is also part of the reason Earth's year-to-year rhythms have remained recognizable for so long. Because the moon's orbit is slightly elliptical, its apparent size in our sky changes, and the moon's brightness and the tides respond to that changing distance. The moon is sometimes nearer and sometimes farther, and that difference is not just a number on a chart. It alters the moon's angular diameter, so the disk can look subtly larger or smaller. It changes the moon's brightness a little, because distance affects how much light reaches you. And it influences tides, because tidal forces depend strongly on distance. When the moon is closer, its pull on Earth's oceans is a little stronger, and the tidal range tends to be larger, especially when the sun's tide is aligned. Over time, people have noticed this and given it informal names, but the deeper point is calmer. The moon's influence is not a fixed setting. It breathes with the orbit in a monthly pattern of nearer and farther, stronger and weaker, all within a stable system. The changes are small enough to be gentle, yet consistent enough to become part of Earth's long tidal pulse. Earthshine is a real illumination of the moon's dark side, and it lets you sense Earth as a bright, reflective world from a lunar perspective. When the moon is a thin crescent, you can often still see the rest of the lunar disk faintly glowing. That glow is sunlight reflected from Earth onto the moon, and then reflected back to your eyes. It is a double reflection, a soft loop of light between worlds. The brightness of Earthshine depends on how much of Earth's dayside is facing the moon, and on how reflective Earth is at that time, with clouds playing a large role. In a quiet way, Earthshine turns the moon into a screen that shows you your own planet's brightness. It also reverses the usual imagination. From the moon, Earth would be a dominant object in the sky, far larger than the moon appears to us, cycling through phases, casting a soft light onto lunar nights. Earthshine is the moon reminding you that illumination is mutual, that worlds can light each other gently, without any lamps at all. The moon's dust can become electrically charged in sunlight, and this can make fine grains behave in ways that feel almost alive, drifting and clinging under simple forces. Without an atmosphere, the lunar surface is exposed directly to ultraviolet light and to the solar wind. These inputs can charge the surface, with sunlit areas tending to lose electrons and become positively charged, while shadowed areas can accumulate negative charge. Along boundaries between light and darkness, the electric environment can change sharply. Fine dust grains, being small and light, can respond to these electrostatic conditions. They can cling stubbornly to surfaces, including equipment and suits, and in certain circumstances, they may even be lofted slightly above the ground. The important insight is that dust on the moon is not just a passive powder. In vacuum, with strong sunlight and energetic particles, electricity becomes a shaping force. The landscape has an invisible field woven through it, and the tiniest grains are the ones that notice first. The moon's surface is continually gardened by tiny impacts, which slowly mix and overturn the upper layers like an extremely patient plough. Every day, micrometeoroids strike the moon at high speeds. Most are too small to make a crater you would ever notice in a photograph, but they are energetic enough to chip, melt, and scatter grains. Over time, this constant tapping churns the regolith, mixing material from different depths and gradually burying some surfaces while exposing others. It means that even in a world without wind or rain, the top layer is not static. It is being worked on continuously, just at a pace that feels almost geological in its gentleness. This is why surface exposure ages matter, why fresh craters look different, and why the moon's soil contains a complex blend of fragments from many places. The moon's quietest change is not a shifting coastline or a flowing river. It is a continual rearrangement of dust and rock caused by impacts too small to hear, accumulating into a slow, persistent stirring. Some lunar rocks break down not mainly by chemical weathering, but by thermal fatigue, as the slow cycle of heat and cold makes minerals expand and contract until they fracture. On Earth, water often finds its way into cracks, and chemistry weakens minerals, and life can pry surfaces apart. On the moon, the stresses come largely from the temperature swings. As sunlight slowly warms a rock face, the outer layer expands. As darkness returns, it contracts. Minerals within a rock expand at slightly different rates, and those tiny mismatches create internal stress. Over enough cycles, microcracks form and grow. The rock can flake, spool, and break down into smaller fragments, feeding the regolith. This is a quiet kind of erosion, driven by physics rather than chemistry. It is the moon showing that even without air or water, time still finds a way to turn solid stone into dust, using nothing more dramatic than repeated warming and cooling under a steady, slow sun. The far side of the Moon is one of the quietest radio environments near Earth, because the Moon's bulk blocks much of our planet's radio noise. Earth is a busy broadcaster. Natural lightning, human communications, and many other sources fill near-Earth space with radio signals. On the lunar far side, the Moon itself stands between a receiver and those emissions, creating a sheltered region. This matters because radio astronomy often seeks faint signals that are easily drowned out. A quiet zone could allow observations that are hard to do near Earth, especially at very low radio frequencies that our ionosphere blocks. The Moon becomes, in this sense, not only an object to study, but also a tool for studying the universe, a physical shield that creates a calm pocket in which weak whispers can be heard. It is another way the Moon participates in systems beyond itself, shaping what can be detected simply by being where it is. And in that sheltered quiet, with the Moon turning the same face away from us as faithfully as it turns the other toward us, you can feel the Earth-Moon pair as a kind of slow hinge in space, opening and closing the view, alternating between noise and silence, light and shadow, and carrying its steady motion onward without interruption, as if the system were designed to keep time gently, even when no one is counting. The Moon's gravity raises tides in Earth's solid crust as well as in the oceans, and the ground beneath you is flexing by small amounts on a lunar rhythm. We tend to picture tides as purely watery, but Earth is not perfectly rigid. The Moon pulls on the whole planet, and rock responds, just more subtly than water does. The crust lifts and settles by small distances, and the timing follows the same basic cycle as the ocean tides, with local variations depending on geology. This matters because it shows how gravity couples directly into the structure of a world. Earth is not a static platform with a moving sea on top. It is a slightly breathing sphere, responding to an external companion. Over long time, that flexing dissipates energy as heat, contributing to the slow exchange that is lengthening our days. And on a quiet night, it can be calming to remember that the Moon's influence is not only out there in the water, it is also in the bedrock, moving gently, too small to feel, but always present. The Moon's slow recession means that ancient eclipses looked different, and in very deep time, the Moon would have covered more than the Sun, making totality more generous. As the Moon moves away, its apparent size gradually shrinks. If you imagine the clock running backward, the opposite happens. In the distant past, the Moon's disk would have appeared slightly larger in the sky. Total solar eclipses would have been more likely to be truly total, with a wider path and longer durations, because the Moon could cover the Sun with more margin. This is not about nostalgia for lost spectacles. It is about understanding that the sky's geometry evolves. The interplay of orbits is not frozen. Alignments that feel timeless are actually time-dependent outcomes of a slowly changing system. The Moon teaches you that even the most iconic celestial events are part of a drifting configuration, like a familiar song played in a slightly different key as the years stretch out. The line where day meets night on the Moon is a moving band of extreme contrast, and it is one of the best natural laboratories for watching heat flow through dust and rock. At the terminator, sunlight arrives at a shallow angle, shadows stretch, and temperature gradients become sharp. A sunlit slope may warm while a shaded floor remains cold, and the difference can be dramatic across a short distance. Because there is no atmosphere to mix heat, the surface is forced to manage its energy by radiation and by conduction into the regolith. Instruments can watch how quickly the ground warms after sunrise, how quickly it cools after sunset, and how insulation changes with grain size and packing. The Terminator becomes a slow-moving experiment that repeats reliably month after month. It shows heat not as a vague warmth, but as something that moves slowly through material, tracing the hidden properties of a landscape you can barely see. Some of the moon's most puzzling bright markings, called lunar swirls, may be linked to magnetic anomalies that subtly shield the surface from the solar wind. In several places, the moon shows pale, sinuous patterns that do not match crater rims or lava flows. They look like delicate brushstrokes on the regolith. One idea is that these areas sit above local magnetic fields preserved in the crust. Those fields are not strong enough to create a global magnetosphere, but they may deflect some charged particles from the solar wind. If fewer particles strike the surface, space weathering may proceed more slowly, and the soil stays brighter for longer. The swirl, then, is not painted by something added. It may be preserved by something withheld, a small reduction in exposure that keeps the surface looking younger than its surroundings. It is a quiet example of how invisible fields can leave visible signatures, and how a world without air can still have subtle forms of protection. The moon's long, winding channels and rills can reveal ancient flows of lava, and some may mark collapsed lava tubes that once carried molten rock beneath the surface. On the moon, lava did not flow like a river in air. It moved under vacuum, and it cooled into basalt plains. In places, you can see channels that bend and meander, suggesting sustained flow, and in other places, you see roofed conduits, lava tubes, that may have drained and left behind hollow spaces. If a tube's roof collapses in segments, it can create a chain of pits or a sinuous depression. This matters because it speaks to the moon's volcanic past in a structural way. Volcanism is not only a smear of dark rock, it is plumbing, roots, conduits, and the physics of cooling. It also hints at environments that are naturally sheltered from radiation and temperature swings, not because the moon provides comfort, but because geometry provides cover. The moon's ancient lavas may have left behind empty architecture, quietly enduring. The moon's poles contain places of near-perpetual light, as well as near-perpetual darkness, because the sun skims the horizon and small changes in height matter enormously. Near the poles, sunlight does not rise high overhead. It circles low, grazing ridges and crater rims. A modest high point can catch sunlight for much of the lunar year, while a nearby hollow may never see it. This creates a landscape where illumination is a property of topography rather than time of day. The consequences are practical and scientific. Sunlit peaks have more stable access to energy, while permanently shadowed regions can become cold traps for volatiles. The poles are therefore not just the ends of the moon, they are special zones where light itself becomes a resource, and where shadow becomes a storage condition. The moon's extremes here are not created by storms or seasons. They are created by the angle of a distant sun and the slow turning of a tilted orbit. The moon's low gravity makes debris from impacts travel farther, so a single crater can seed its surroundings with material from depth, spreading a geological fingerprint across a wide area. When an impact excavates rock, it throws material outward in an arc. On Earth, Air resistance and higher gravity limit how far that material can travel, and erosion soon mixes it away. On the Moon, in vacuum and with lower gravity, ejecta can travel long distances and land softly enough to remain identifiable for a long time. This is why crater rays can extend so far, and why samples collected in one place may contain fragments from distant impacts. The lunar surface is, in a sense, cross-contaminated by history. Each big collision does not only make a new feature, it redistributes old layers, placing deep material on the surface where it can be studied. The Moon becomes a naturally drilled world, with impacts acting as excavators that bring buried chapters up into the light. The Apollo seismometers revealed that the Moon has a layered interior, and the way seismic waves behaved helped show how dry and rigid the lunar body is compared to Earth. Seismometers placed on the Moon listened to impacts, to small moonquakes, and to the long ringing that followed. From the travel times and patterns of waves, scientists could infer changes in density and composition with depth. The Moon is not a uniform ball of rock. It has layers and likely a small core, and a mantle that cooled early. But the listening also revealed the Moon's distinctive ringing. Without oceans, without thick atmosphere, and with a colder, stiffer crust, the Moon can sustain vibrations in a way that feels almost musical, though far below hearing. This matters because it gives you a sense of the Moon as a physical object with a mechanical personality. Not alive, not active in Earth's way, but still responsive, still capable of carrying energy through its body, and still able to tell its structure to anyone patient enough to listen. And as you hold that idea of listening, of a world that answers with vibrations and timing rather than with weather and noise, you can let the Moon feel less like a distant lamp and more like a steady instrument in space, turning slowly, reflecting softly, and keeping its quiet rhythms as it moves through darkness and sunlight, continuing on and on. The Moon has an atmosphere of sorts, but it is so thin that its particles rarely collide, and instead follow quiet ballistic hops across the surface. Around the Moon, there is a tenuous exosphere made of individual atoms and molecules that can be knocked free from the surface by sunlight, impacts, and the solar wind. In an ordinary atmosphere, particles bump into one another constantly, sharing energy and forming winds. On the Moon, a liberated atom can rise, arc through a vacuum, and land somewhere else without meeting anything on the way. It is less like air and more like a slow, sparse migration. Some atoms are lost to space entirely, some settle back into the regolith, some drift into long, faint tails that can extend away from the Moon under the pressure of sunlight. This matters because it changes the meaning of atmosphere. The Moon shows you a limit case, where gas exists, but behaves more like a collection of individual travelers than a fluid. Even emptiness here is not perfectly empty. It carries a thin, shifting trace of matter. The Moon can grow a long, delicate tail of atoms that stretches far from its body. And this tail is shaped by sunlight and by the Moon's passage through space. When atoms such as sodium are released from the lunar surface, they can be pushed by sunlight, not with a force you would notice in daily life, but enough to matter in a vacuum over time. As the Moon orbits Earth, and Earth orbits the Sun, these freed atoms can form an extended cloud, and in the right conditions, a faint tail pointing away from the Sun. It is not a plume like smoke, because there is no surrounding air to carry it. It is more like a slow, invisible stream. The idea is soothing because it is so gentle. Light, which feels weightless, can shape matter at scale. The moon, which seems so solid, can shed a subtle veil that is carried outward, a reminder that even a quiet world is exchanging particles with the space around it. The moon's gravitational field is lumpy in ways that reveal buried structure, and mapping those lumps is one of the best ways to see what lies beneath the surface without drilling. When spacecraft orbit the moon, their paths are perturbed by tiny variations in gravity. A dense region pulls a little more strongly. A fractured region pulls a little less. By tracking a spacecraft's motion with extreme precision, you can infer a map of gravitational variation, like feeling the texture of a surface with a blindfolded hand. When this has been done in detail, it has revealed that impact basins and ancient structures are not just visible scars. They correspond to deep changes in the crust and mantle, including regions that were densified or uplifted long ago. The moon, then, can be read in two layers. There is the visible face of craters and plains, and there is the invisible face of mass distribution, a hidden landscape of weight that still shapes motion today. It is another way the moon serves as an archive, holding memory not only in its appearance, but in its gravity. The moon's crust carries the signature of enormous impacts that fractured it deeply, and those fractures may have influenced where later volcanism could reach the surface. A large impact does not merely dig a hole, it sends shock through the crust, cracking and weakening rock over vast areas. In a young moon that still contained heat, such weakness could become a pathway. Melt rising from below would find it easier to travel through damaged, fractured regions than through intact, thick crust. So, the scars of bombardment and the pattern of later lava flows are not independent chapters. They can be connected, with impacts preparing the routes through which volcanism later expressed itself. This is a calm, structural idea. One event changes the permeability of a world. A later event follows the easier path. Over immense time, the surface ends up recording an interaction between violence and flow, between sudden fracture and slow filling. All of it guided by the moon's quiet physics. Some lunar soils contain tiny glass beads formed in ancient fire fountain eruptions, and these beads preserve a record of the moon's interior volatiles in a way that solid rock does not. Volcanism on the moon was often basaltic, and in some episodes it may have involved jets of molten material thrown upward, cooling rapidly into glass droplets. These droplets fell back as beads, mixing into the regolith. The important part is what rapid cooling can trap. In a moment, gases and volatile components can be sealed into glass, storing chemical information from the erupting melt. Over billions of years, that glass can remain in the soil, protected from weather and biology, though not from space weathering. When scientists study these beads, they are not just admiring a texture. They are reading an interior message, a faint clue about what the moon once contained, and how it lost heat and gases over time. In a quiet way, the moon is offering samples of its ancient breath, captured in small, cooled spheres. The moon is a stable reflector of sunlight, and its surface has been used as a reference for calibrating instruments, because its reflectance changes slowly and predictably. Many things on Earth are difficult to use as standards. Clouds change, landscapes shift, the atmosphere interferes. The moon, by contrast, provides a long-term target whose broad reflective properties are comparatively steady. Of course, it is not perfectly uniform, and it has its own subtle changes with angle and phase. But those behaviors can be characterized. This makes the moon useful as a kind of natural calibration lamp for monitoring instruments over time. There is something quietly fitting about that. A body that has no purpose and no intention can still become a reference point for precision, simply because it is consistent. The moon helps humans measure not only time, but the reliability of our own eyes and machines. The moon is still being struck by meteoroids today, and some impacts produce brief flashes that can be observed from Earth, turning the lunar surface into a screen for ongoing solar system traffic. Even now, space contains small debris moving at high speeds. When a meteoroid hits the moon, the energy can generate a momentary burst of light, a tiny spark against the dark. Because the moon has no thick atmosphere to burn objects up, more of these small bodies reach the surface. Watching for these flashes is a way to estimate impact rates and to understand the environment through which Earth also travels, though Earth is protected by air. The idea can be oddly calming. It means the solar system is not quiet in the way a room is quiet. It is quiet in the way space is quiet, with occasional tap and strike, rare and brief, absorbed without sound. The moon simply takes the hits, marks them, and continues. The problem of communicating with the moon's far side teaches you something practical about geometry, and it is why orbiting relay spacecraft become part of lunar exploration. The far side is not hidden by distance. It is hidden by the moon itself. Radio signals travel in straight lines through space, and the solid body blocks the line of sight. So, if you place a lander on the far side, it cannot speak directly to Earth unless something else is positioned to pass the message along. A relay in lunar orbit, or in a carefully chosen looping orbit near the moon, can keep a partial view of both Earth and the far side surface, acting as a quiet intermediary. This is not a dramatic limitation. It is a simple consequence of shape. It is the moon reminding us that exploration is often about vantage points as much as power, and that in space, being in the right place can matter more than being strong. And as you picture these gentle relays and faint atomic tails, you can let the moon feel less like a single object and more like a region of influences, gravity shaping orbits, light shaping atoms, impacts shaping dust, and everything moving slowly through the dark with steady patience, as if the entire system were content to keep unfolding at its own unhurried pace, carrying each small change forward into the next. The moon preserves the earliest chapters of our neighborhood because it has been so quiet for so long. On Earth, the ground is busy, plates move, water cycles, air works like a slow file, rubbing down edges, carrying grains away, laying new layers over old ones. The moon does not do those things in the same way. Its surface is altered, but it is altered gently, and mostly from above. So, when you imagine the moon, you can also imagine a kind of patience, a crater rim that has waited for ages, a lava plain that cooled, and then simply remained. It is one of the few places near us where deep time stays visible, not as an abstraction, but as an actual landscape. Not everything is preserved. Dust is stirred. Rays fade. Small impacts keep arriving. But the overall story is not constantly overwritten. It is allowed to sit and to be read quietly. The moon's orbit is slowly changing, and the system keeps time even when no one is watching. Every month, the moon makes its circuit, and every month, it does so from a slightly different distance than before. The difference is tiny, far smaller than the width of your hand at arm's length. Yet the change is real. It accumulates. It is part of the same exchange that gently slows Earth's spin. This is how the moon teaches you to think about change that is too slow to notice. Not the sudden change of weather or news or a single event, but the steady change of systems. The kind that continues through generations without asking permission. When you hold that in mind, the moon becomes a calm reminder that time is not only what we count, time is also what happens quietly in the background, shaping relationships by degrees. The boundary between light and shadow on the moon is one of the clearest ways to see the surface as a three-dimensional place. In bright, full light, the moon can look like a smooth disk, almost painted. But as the phase changes and the terminator slides across, relief appears. A crater rim lifts into sunlight while its floor remains dark. A ridge becomes a line. A mountain becomes a small island of brightness, separated from daylight by a sea of shadow. It is not only beautiful, it is instructive. It shows you that what you perceive depends on angle, and that the simplest changes can reveal structure. The moon does not need to alter its shape to look different. Light alone can redraw it, night after night, with slow consistency. The moon's surface is not truly still, because tiny impacts and radiation continually reshape the topmost grains. It is tempting to call the moon frozen, but even the quietest world is active at the smallest scale. Fine dust is chipped and stirred. Glassy coatings form and are broken. The upper layer is mixed and remixed, as if a very gentle hand were turning soil that never grows anything. Over long spans, sharp edges soften, contrasts fade. The surface becomes a record not only of big events, but of innumerable small ones. This is a calmer kind of activity. It does not roar, it does not rush, it simply continues. And it means that even a place with no wind and no rain is not outside of change. It is simply changed by different forces on different timescales. The moon carries human traces that may last for a long time, and they sit within a landscape that will outlast them. A landing stage, a set of tracks, a small tool left behind. These are faint details on a world, and yet they are meaningful because they mark a brief moment when Earth reached out and touched a nearby companion. The moon did not become ours, and it did not become less itself. It remained a world of dust and stone, turning in silence. But it did receive those small marks. They are part of the moon's long archive now, folded into a surface that has recorded impacts, lava flows, and cosmic weather for billions of years. Human presence becomes one more thin layer in a very thick story. Not dominant, not permanent in every detail, but real and quietly humbling. The moon's poles are places where sunlight can be scarce or plentiful for long stretches, making light itself feel like geography. In those high latitudes, the sun stays low. A small rise can catch it again and again, while a nearby hollow stays dark for years. You do not need storms to create extremes. You only need an angle. It is one of the gentlest demonstrations of how the universe works, how a small tilt and a slow orbit can arrange heat, cold, and shadow into persistent patterns. When you think of the moon that way, it becomes less like a simple sphere and more like a world where basic geometry writes the climate, and where day and night are not fleeting but lingering states. The moon's apparent calm is a kind of honesty because it shows physics without many disguises. On Earth, so many layers sit between cause and effect. Air softens light. Water blurs edges. Biology hides rock under green. The moon removes many of those layers. Light falls where it falls. Shadows form where they must. Heat arrives and leaves by simple routes. Dust behaves according to small forces that are usually overwhelmed on Earth. It is not a better world. It is not a kinder world. But it is a clear world, and that clarity is part of its quiet appeal. When you look at it, you are not only looking at a place, you are looking at an arrangement of laws playing out in a clean environment, steady and uncomplicated. The moon has been a companion to human timekeeping, not because it tries to be, but because its rhythm is easy to notice and hard to ignore. Long before precise clocks, the phases provided a repeatable pattern. The month was written in the sky. It did not match the year neatly, and that mismatch taught humans something about the world. That different cycles can overlap without aligning. That time can be layered. That nature keeps several rhythms at once. Even now, when we can measure time with atoms and electronics, the moon still carries that older kind of time. A slow, visible cycle that your body can notice without numbers. A thin crescent, a bright half, a full disk, and then the return, over and over, with gentle regularity. And once those last details settle, you can let them become softer. You do not need to hold them tightly. They can simply be there. Because the moon is not only an object of study, it is also an experience. From the surface of Earth, it is a steady presence, sometimes bright, sometimes faint, sometimes gone behind cloud, but always returning. It hangs in the sky in a way that feels close, even though it is far enough to contain its own mountains and plains. It makes the night feel shaped. It gives the darkness a focal point, and yet it is always moving, always changing its angle, always carrying its shadowed half with it, always drifting through the same broad pathways, month after month. If you imagine the moon from above, the system becomes calmer still. Earth and moon circling their shared balance, both traveling together around the sun carrying them around the center of the galaxy. Everything in motion, but nothing frantic. Motion does not always mean disturbance. Sometimes motion is the most stable thing there is. The moon's motion is like that, smooth, predictable, unhurried. It turns a little each day. It slides a little through the stars. It changes phase by degrees that your eyes can track. And all the while, it remains a world of quiet extremes. A sky without air, light without haze, shadow without softness, dust without rain. It can help to picture that stillness. A bright slope in sun, a dark crater floor in permanent shade, a plain of old basalt, fine-grained with impacts too small to count, a ridge casting a long shadow that moves only slowly. In that landscape, time behaves differently, not because physics is different, but because there are fewer interruptions, less churn, fewer erasers. So the moon becomes a kind of memory, a reminder that the past can remain present when the environment is quiet enough to allow it. And in a calm moment, you can let that thought widen, because the moon is also a reminder of scale. It is close enough to feel familiar, yet it is far enough to be a separate world. It is large enough to pull oceans, yet small enough that we can hold it in our sky as a disk. It is ancient enough to carry early solar system history, yet near enough that human signals can reach it in moments. That mix of closeness and distance is part of its strange comfort. It sits on the border between the intimate and the vast. When you think about humanity's relationship with the moon, it does not have to be dramatic. It can be simple. For most of human history, the moon was a light, a clock, and a companion, a marker in the sky that made the night feel less empty. Later, it became a destination, briefly, a place reached by careful engineering and patient courage. Then, again, it became mostly a presence. In all of these roles, the moon remained itself. It did not become something else because we looked at it differently. It did not change its rhythm because we learned its mechanisms. Understanding did not diminish it. If anything, it made it steadier. Because when you understand that the phases are geometry, they become even calmer. When you understand that tides are energy exchange, they become even more gentle. When you understand that the surface is an archive, it becomes even quieter. Knowledge, here, does not add noise. It adds depth. And depth does not have to keep you awake. It can do the opposite. It can make the world feel orderly, held. You can picture the moon above you now, wherever it is in its cycle. Not as a symbol, but as a physical body in motion, a sphere of rock and dust, turning at its measured pace. One side facing Earth, not by choice, but by the calm outcome of gravity over time. It is there, and it will remain there, long after this night has passed. Not unchanged, but changing slowly enough to be almost the definition of patience. And you do not have to follow every detail. You can let the words become like a dim light, and let your mind rest in the general shape of the idea. A companion world, a slow orbit, light and shadow taking turns. In the background, Earth turns, one rotation after another, oceans moving subtly, pulled and released, the day lengthening by an amount too small to notice, but real all the same. Above, the moon continues its circuit. It rises in different places. It climbs to different heights. It shifts against different star fields. And farther out, the Earth-Moon pair continues around the Sun. A yearly motion so steady that it became the basis of our seasons, our habits, our sense of return. All of it is motion, and all of it is quiet. You can let that quietness settle into you, not as an effort and not as a task, just as a background fact of existence. The universe does not need to hurry. Most of what it does slowly. Worlds form, worlds cool, orbits adjust, light travels, dust shifts, and in the middle of that, a human life gets to look up, to notice, and then to rest. If your thoughts wander, that is fine. Wandering is natural, like the moon's slow drift across a night sky. If you hold on to a single image, let it be simple. The moon in its orbit, the sun's light arriving, a line of shadow moving across a pale surface. No urgency, no demand. Only the steady continuation of things that have been continuing for a very long time. In a sense, the moon is a reassurance written in celestial mechanics. A cycle you can trust. A presence that returns. Not because it cares, and not because it intends, but because gravity is reliable. And in that reliability, you can find a kind of calm. So now, you can let the details fade further. Let the moon become less a subject, and more a quiet companion in the background of your night. A pale disk, a gentle phase, a steady orbit, Earth turning beneath you, the room still, your breathing easy, and above it all, the moon continuing its long habit of motion, the same way it has done for so many nights before. Slowly, silently, faithfully. Good night. May your rest be gentle, and may the quiet rhythm of the moon, moving through light and shadow, carry you softly into sleep.